4.5 billion years ago, the Earth did not have a moon. It had an ocean of molten rock, a surface temperature of several thousand degrees, an atmosphere of vaporized minerals, and it was spinning, much faster than it spins today. A day on early Earth lasted approximately 6 hours. Then something arrived. A planet. Not an asteroid, not a comet. A planet, roughly the size of Mars, which is itself half the diameter of Earth. It had been forming in the same orbital neighborhood as Earth for tens of millions of years, growing from the same cloud of gas and dust, following a trajectory that made a collision not just possible, but, in retrospect, almost inevitable. It hit. The energy released in that collision was greater than anything that has happened on Earth since. The impactor, which scientists have named Theia, after the Greek titan who was the mother of the moon goddess Selene, did not bounce off. It did not pass through. It struck at a glancing angle, and the collision was so violent that both objects partially vaporized. Material from both planets was ejected into space in a ring of debris that surrounded the early Earth. Within months to thousands of years, an eye blink in geological time, the debris coalesced. Gravity pulled the fragments together. They collided, merged, and heated, and from the wreckage of two worlds, a new one formed. That is where the moon came from. Not from captured space rock, not from the early Earth spinning off a fragment. From a collision so catastrophic that it reshaped two planets simultaneously and left one of them orbiting the other for the next 4.5 billion years. For most of human history, the moon's origin was one of the great unanswered questions in science. It was so obviously there, so dominant in the night sky, so influential on the tides, so woven into every human culture that had ever looked up, and yet nobody knew where it came from. Three competing theories occupied scientists through most of the 20th century. The first was fission, the idea that the early Earth spun so fast that it threw off a chunk of itself, which became the moon. The second was capture, the idea that the moon formed elsewhere in the solar system and was gravitationally captured by Earth as it passed by. The third was co-accretion, the idea that Earth and moon formed simultaneously from the same cloud of material as siblings rather than parent and child. Each theory explained some of the evidence. None explained all of it. The fission theory couldn't account for the physics required. Earth would need to have been spinning impossibly fast. The capture theory couldn't explain why the moon's composition is so similar to Earth's mantle. The co-accretion theory couldn't explain why the moon has so much less iron than Earth, given that they supposedly formed from the same material. Then the Apollo missions returned lunar samples, and everything changed. The rock from the moon was chemically similar to Earth's mantle in ways that ruled out an independent origin, but it was also different in ways that ruled out a simple split. The oxygen isotope ratios were nearly identical to Earth's, suggesting the same raw material. But the moon was depleted of volatile elements like water and sodium in ways that implied an enormous heating event. The data pointed towards something that none of the three existing theories predicted. Something violent, something that involved both worlds. The early moon and early Earth were locked in a gravitational embrace so intense that the tidal forces between them were enormous. Those same tidal forces have been gradually pushing the moon away ever since. The moon is currently moving away from Earth at approximately 3.8 centimeters per year, about the rate your fingernails grow. Over 4.5 billion years, that adds up. The giant impact didn't just create the moon, it fundamentally altered the Earth in ways that may have made life possible. The collision tilted Earth's rotational axis to approximately 23.5 degrees, the tilt that gives us seasons. Before the impact, Earth's axis may have been nearly perpendicular to its orbital plane, which would have produced an entirely different climate system. The moderate tilt we have, enough to create seasons, not so much as to produce catastrophic temperature extremes, is a direct consequence of that collision. The moon also stabilizes Earth's axial tilt. Without the moon's gravitational influence, computer models suggest that Earth's tilt could wobble chaotically between nearly 0 and over 85 degrees on timescales of millions of years, producing climate shifts so severe that the stable conditions required for complex life to evolve might never have persisted long enough. The moon we look at tonight is not a coincidence. It is not a beautiful accident. It is the product of a specific catastrophe that occurred at a specific moment in Earth's history that altered our planet's axis, its rotation, its tides, and its long-term climate stability in ways that may have been essential prerequisites for everything that came after, including us. The giant impact hypothesis is the consensus, but science is always honest about what remains uncertain. The biggest open question is Theia itself. If Theia struck Earth and merged with it, where is Theia's material? The answer may be inside us. A 2021 study published in Nature proposed that two continent-sized structures deep in Earth's mantle, known as large low-shear velocity provinces, sitting at the boundary between the mantle and core, may be remnants of Theia's mantle that never fully mixed with Earth's. If this is correct, pieces of the impactor are still sitting inside the Earth, 2,900 kilometers below the surface, having been there for 4.5 billion years. Science advances at the edge of its own uncertainty. The giant impact hypothesis is not in doubt, but the details of what happened, the exact angle of impact, the precise composition of Theia, the mechanism by which the debris ring coalesced so quickly, are still being refined by every new mission, every new simulation, every new deep Earth seismic study. The moon is still telling us things we didn't know. There is a certain kind of awe that comes from understanding the origin of something you thought was simply there. The moon has been in the human sky for as long as there have been human eyes to see it. It shaped the tides that shaped coastal ecosystems. It gave us the calendar. The word month comes from moon. It lit the nights of every civilization that ever existed. It has been in every myth, every love poem, every navigation chart ever written. And it exists because two planets collided. Not gently, not constructively, catastrophically. In an event that, had there been anyone to witness it, would have looked like the end of everything. This is something the universe does repeatedly. The things that appear most permanent and most beautiful are often the products of violence so complete that it would be unrecognizable to us. The carbon in your body was forged in the core of a star that exploded. The iron in your blood was made in a stellar collision. The moon that hangs in the sky tonight was born from a planetary catastrophe that reshaped two worlds. The universe builds through destruction. And what it builds from destruction has a tendency to outlast everything that was there before. 4.5 billion years ago, something hit us. And instead of ending us, it gave us a companion. One that would stabilize our seasons, slow our days, pull our oceans back and forth, and light our nights for as long as both objects exist. That is not a small thing. That is everything. The next time you look at the moon, consider what you're looking at. Not a rock in the sky, not a beautiful coincidence. A world that was born in fire from the wreckage of a collision that remade this planet. A world that has been slowly moving away from us for 4.5 billion years, retreating by the width of 2 fingers every year in no particular hurry. It will be visible from Earth for billions of years to come. Long after we are gone, long after the last person looks up at it, the moon doesn't need us to witness it. It was there before we were. It will be there after. But we are the first thing in 4.5 billion years that looked up and understood where it came from.